today is the next section on magnetism. We're going to look at electromagnetic induction. Specifically in today's video, we're going to look at the idea that we can use magnetic field to generate current. We're going to talk about magnetic flux, and we're going to talk about how to calculate the magnitude of that induced current, and then later in the week we're going to talk about Lenz's law. Now, remember I said last week that Oersted, who discovered accidentally that a current-carrying wire produces a magnetic field, started a whole flurry of activity in magnetism. Remember, Ampere started to look at the motion of charged particles in magnetic field. Well, another guy, Michael Faraday, wanted to know, well, if current can produce a magnetic field, can a magnetic field produce current? So can we go the other way? Now, Michael Faraday set up this setup with a battery and a wire, and he used an iron bar, and you're going to see next week in lab that metal conductors actually amplify magnetic field, and that was the point of this iron donut here. And he wrapped the wire around that bar, and then on the other side he wrapped another wire and hooked it to an ammeter. Now remember, an ammeter measures current, and back in the day, ammeters had needles that deflected. They weren't those nice meters that read digital displays and tell you how much current you have, but the needle would deflect at a certain angle, and that would tell you how much current you had. So Michael Faraday set this up, he closed the switch, he looked at the ammeter, and nothing. Opened the switch, looked at his setup, closed the switch, nothing. But out of the corner of his eye, you notice that in the process of opening and closing the switch, when he closed the switch, he got a small deflection. And when he opened that switch, he got a small deflection. So what Michael Faraday discovered is that current can be induced in a conductor, in a wire, if and only if the amount of magnetic field passing through that conductor is changing. So there has to be change. If the magnetic field's constant, that switch is closed, nothing. But in the process of opening and closing the switch, he got current to be generated. That's what we're going to talk about today. So we're going to start basic and look at taking a piece of metal, like an iron bar, and moving it through a magnetic field. So here's my magnetic field, those X's into the page is my magnetic field. So here's my metal bar, and a metal bar has a bunch of protons and electrons in it, right? So it's full of charge, right? And if I start to move that metal bar that's full of charges through this magnetic field, right, now I have motion of charged particles in a magnetic field, and they're going to feel a magnetic force. So I move it with some speed through this magnetic field, and I generate a magnetic force, right? And the direction of that force, right, by the right-hand rule, get your right hands out. Magnetic field is into the page. We're moving the bar down, right? We're taking this bar, we're moving it down. Palm, force on positive, right? Knuckles, force on negative. So I'm going to start accumulating positive charges over here, and the electrons are going to be moving over there. So I'm going to get this charge separation. Now, once I've got this charge separation, right, I generate an electric field inside my bar. So take my bar, start to move it, right, it's full of electrons. I generate a magnetic force, which forces all the electrons to one side of the bar, leaving the other side with a net positive charge. And that charge separation generates this electric field. Now that I've got an electric field, if I just took a wire, right, another conductor, to either ends of this bar, right, now I have a circuit. And now I have a place for those electrons to move it, and they're going to start to move. Now, right, when I separate these charges, right, and I have this electric field, I now have electric potential, right, voltage. And from our equation from electrostatics, right, the change in voltage is equal to E times delta X, and in this case, delta X here is the length of my bar, right? There's my delta X. Now, as I move this bar, right, the charges separate. They stop moving when the magnetic force, QBB, is equal to the electric force, E times Q, electric field times the charge. Right, this is the equation for magnetic force, QBB. which means that I have an electric field, right, E equal to BB, right, and E, electric field, is equal to the voltage over the length of the wire, right, delta B divided by delta X, move my L over there, right, and I get this, the voltage in the bar, right, that's voltage, is equal to the velocity of the bar times the length of the bar times the magnetic field that bar is in. We call this here, this squiggly E here, right, our ideal EMF, when we talked about circuits, we call that the motional EMF, because I'm creating this voltage by motion. So if I connect a wire to these ends, right, now I have a loop, I get current to flow, and the flow of current comes from this motional EMF, this voltage that I've set up in my conductor. And that EMF, that voltage, is equal to the velocity of the bar times the length of the bar times the magnetic field that the bar is exposed to. Once I have voltage, right, I have current. So if we go back to our last unit, right, here's my motional EMF equation, right, current is the amount of voltage divided by the resistance in the circuit. So here is my voltage divided by the total resistance of my circuit. That'll tell me how much current is flowing in my circuit. Now, an application of this, here, one is a railgun, but here we have a conductor, right? This is a piece of metal here in a U shape, and here's my metal bar, right? When it's sitting on this conductor, right, I have a circuit. I have a place for charge to flow. So as I move this bar to the right here, in that magnetic field, right, magnetic field into the page, bar moving to the left, right, I'm going to force positive charge up or negative charge down, right, and then I have current, right, the flow of positive charge is current. I'm going to have current flowing counterclockwise. The amount of current that flows is equal to the voltage I create through the motion of the bar in the field divided by the total resistance. V is equal to IR. Metal bar on a metal rail, start to move it in a magnetic field, and you're going to generate current. As long as you keep moving. Now, the thing is, once we start moving this, right, once I have current flowing, I have another force, right? I have force on my current in my magnetic field. Which means that if I stop pulling this bar, if I stop physically moving this bar in this direction, it's going to stop, right? Because it's feeling an opposing force. As soon as I start to pull this bar, right, now I have current running up here in the conductor. So by the right-hand rule, the force rule, right, current's going up, magnetic field's to the into the page, which means I'm generating a force to the left, a magnetic force. And in fact, no matter what I do, right, if I start moving the bar this way, right, then I'm going to actually have current going down, but again, magnetic field is going to oppose the motion of my hand. So anytime I start to move this conductor in a magnetic field and I generate current, I'm going to also generate an opposing force. So if I want to move this object at constant speed, right, at constant speed, the sum of the forces have to equal 0, which means that my pulling force will equal the magnetic force. So if I ask you to solve for the magnitude of the force of pulling on this bar to keep it at constant speed, well, you're just going to calculate our good old Flib equation. Right? Force is equal to current in the wire times the length of the wire times B. Now the length is the important part. The length here is going to be the length of this bar. All right, that's the thing that we're moving. That's the thing that's feeling the force that is opposing our force of pulling. So that length is going to be the bar length. All right, let's do a calculation. I have a rod that is 12 centimeters long, and it's pulled at a speed of 15 centimeters a second, not meters, centimeters a second. If the magnetic field is 0.8 Tesla, what is the motional EMF developed in the rod? All right, EMF, squiggly E, V, L, V. All right, we have our velocity, but make sure you put that in meters per second. So divide by 100. Convert that, well, maybe we don't need to. Do we need to? Yeah, I guess let's work in meters. Convert that into meters and multiply by the magnetic field. If we do that, if you do that correctly, you're going to get 1.44 times 10 to the negative 12 volts. So we're generating voltage, motional EMF. What is the magnitude and the direction of the electric field that's generated inside our metal bar? Well, remember that, right, delta V is the electric field times delta X. We've got our voltage now, right? Here's our voltage. We're going to divide that by the length of our wire in meters. But what is the direction? So remember, from a definition standpoint, that the direction of the electric field points from positive to negative. So let's take a look. Here's our bar. It's moving to the right, so our thumb needs to be to the right. The magnetic field here is coming out of the page, right? Dots are coming at you. So you want to put your hand like this. Out of the page, thumb to the right. Positive charges down, negative charges up. Right? We follow the direct, so positive charges down, negative charges up, right, means that my electric field is pointing up. Right? Positive charges here, negative here. Electric field lines point from positive to negative. So take your voltage, divide by the length of the wire, and you'll get the magnitude of your electric field. Units for volts per meter, newtons over coulomb, same thing. And of course the electric field is up. Right-hand rule. All right, now let's throw a wire on this. Let's put this conducting bar on a rail. Now we're going to pull it so that it moves with a speed of 1.6 meters per second. The rod itself is 30 centimeters or 0.3 meters. Ooh, now I've got a resistance. It has a resistance of 2.4 ohms, the magnetic field 0.35 Tesla. Ooh, and the resistance, this conductor that it's sitting on also has a resistance. 25 ohms at any given instant. First, we're going to calculate the induced EMF. Right, so we're going to do EMF, right, is VLB. Velocity we have, 1.6. The length, right, put that in meters, so 0.3 times our magnetic field, 0.35 Tesla. All right, and you get 0.168 volts. I'm guessing we're going to calculate current next. What is the current in the conductor? All right, so current, right, is going to be the voltage divided by the resistance. But I got two resistance values. I need to know how to put them together, right? Because this needs to be a total REQ, a total resistance. Are they in series together or are they in parallel? How do you know? Draw the current flow. Right? We follow positive charge around, right? So our positive charges are down here. Right? And so here goes the current. Are those in series or parallel? Is there one path or is there a junction? right? There is one path, meaning they're in series, which means I just need to add to get the two together, right? So I'm going to take my 0.168 volts, and my REQ is going to be 2.5 from the conductor, the moving rail, plus the 25, that's the stationary rail. So 0.168 divided by 27.5. I guess I should erase what I wrote so you can actually see. And you should get 6.1 times 10 to the negative third amps. All right, so now I know my current. What else do we ask? How about the magnitude of the pulling force that keeps us moving at constant velocity? All right, if I pull this bar, right, in the magnetic field I generate current. Once I generate current, I generate a magnetic force that's opposing my motion. So how much do I need to pull this with? What kind of force do I need to pull this with to keep the velocity constant? Well, if it's moving at constant velocity, right, sum of the forces equals 0, which means the force of my pull must equal, I don't know why I pulled it. This has to equal the magnetic force, right? Magnetic force being flip. All right, so take the magnitude of your current, multiply by the length. The length is the thing that we're pulling, that length, times B, the magnitude of our magnetic field. So 6.4 times 10 to the negative fourth newton. So I don't have to pull very hard, do I? All right, so let's get back to what Faraday discovered. Right? Faraday discovered that changing magnetic field induces current, not stationary. So first we looked at that by changing the amount of magnetic field through this circuit, right, by moving the conducting bar. But we need to classify this change somehow. Current is induced when the magnetic field passing through that coil, right, that loop, that closed circuit, right? Current's not going to flow if there's not a closed loop. And it only will induce current if the amount of magnetic field is changing. So we need to quantify that change somehow. So Faraday came up with this idea of flux. Now, if we think about the amount of magnetic field, right, in order to quantify it, first we have to figure out how much magnetic field is flowing through a certain area. And so if I have a loop, right, the amount of magnetic field passing through that loop, one, depends upon the orientation of the loop to the field. All right, if my magnetic field is straight, right, perpendicular to the surface of the loop, right, looks like that, then all of the magnetic field is going through the loop. But if the loop is at an angle to the magnetic field, then not all of the field is passing through the loop. And in fact, if it's oriented like this to the magnetic field, right, there's no magnetic field going through the loop at all. Also, how much magnetic field going through the loop, of course, depends upon how big the loop is, or the area of the loop. So what magnetic flux is it's a measure of the amount of magnetic field passing through an area A. So Faraday came up with this idea of magnetic flux, being the flow of magnetic field through my loop, right? And the amount of flux, of course, depends upon the area, how much room there is for the flux to move through, and how much magnetic field is passing through in terms of its orientation to my loop. So magnetic flux definition is the amount of magnetic field passing through a loop of area A. So let's take a look at that. So here I have a loop, right, of area A, and there's my magnetic field passing through. Now, how do we determine the amount of magnetic field? Right, we could just count the number of lines. Okay, not very practical, but yeah, sure, we can do that. All right, so here I have a uniform magnetic field passing through a loop of area A. So in this case, all of the magnetic field passing through that loop is going through the loop here. So I would calculate magnetic flux, phi, and we should probably put phi sub B, is equal to the amount of magnetic field that's present times the area of the loop. Magnetic flux is the amount of magnetic field passing through an area of area A. But what if I start to rotate this loop? Right? You can see that as I start to rotate this loop, I now don't have all of the magnetic field passing through the area. So when we quantify how much magnetic field is passing through this loop, we're going to have to use some trigonometry. When it's at an angle, magnetic flux is the amount of magnetic field B passing through the loop of area A times the cosine of the angle the magnetic field makes with the normal of the loop. That's not the surface of the loop, right? It's not this surface. It's a normal line, right? Remember, normal lines are lines that are perpendicular to a surface. So here would be the normal line for this loop. So the angle here in this equation is the angle between the normal line to the loop, right, which would be perpendicular to the loop. So if I turn the loop like this, right, it's like that. There's my magnetic field straight up. So the angle we use is that angle, not to the surface. So that angle is the angle between the normal and the magnetic field. Just like when we do the law of reflection, right, when we were doing optics, law of reflection, we're talking about the angle of incidence and refraction compared to the normal line, a line perpendicular to the surface of whatever is reflecting, so the mirror, for example. Magnetic flux also has a special unit, just like magnetic field has a special unit of Tesla. The unit of magnetic flux is a Weber. All right, a Weber would be a Tesla times a meter squared. Weber. All right, let's do some calculations of magnetic flux. So here I have a loop that has an area of 40 centimeters squared. The line here, here's the magnetic field. Magnetic field is 3 Tesla. It is pointing directly to the right, and I have my loop here with its area of 40 centimeters squared at different angles. So here is the loop in this orientation, right, which means that all of the magnetic field is perpendicular to the surface of the loop, which means it's parallel to the normal line, right? The normal line is that line that we're interested in. Right? Here I have maximum amount of flux, angle 0. What about here? Right? In this scenario, I have no magnetic flux, right? Cosine of 90, 0. Here, I don't have all of my magnetic field like I did here, but I still have some flux. All right, so when we go to calculate, all right, in my first scenario, BA cosine theta, the cosine of 0 is just 1, so I just take 3 and I multiply by the area. Of course, that's 40 centimeters squared. Make sure you convert appropriately. That would be 0.004 meters squared. So that's 12 milliwebers. Milliweber. That's a whole unit. Here is, right here, there's no magnetic field passing through the loop. So it's 0. That's the cosine of 90 is 0. Here's BA cosine of 60, right? Cosine of 60 is a half. So we have half as much of our milliwebers. Milliwebers, right, times 10 to the negative third. Maximum flux, 0 flux, half as much flux. All right, we're going to stop here. And when we come back, we're going to talk some more about Faraday's observations.